Today, I'd like to talk about the Coriolis Force and demystify the physics underlying this topic. If you're watching this video, you might be familiar with the experiment where you grab onto something heavy, sit on a swivel chair, and start spinning. You will notice that if you hold your arms out, the spinning slows down, but if you pull your arms in, it speeds up again. This experiment illustrates the conservation of angular momentum. Angular momentum, which we usually denote as L, is a property of orbiting bodies, which measures how hard it is to halt their orbit. It depends on r, the distance to the axis of rotation, m, the mass of the body, and omega, the speed of rotation. Let's think about what it means for L to be conserved. The reason that we define L in this way is that it has the useful property that when there are no external torques, it stays constant, no matter how we adjust omega, m, and r. Mathematically, this means that the derivative of L, how quickly the angular momentum changes with time, is zero, because it isn't changing at all. So let's see. If r and omega depend on time, then we can actually get an expression for this derivative. Applying the product and chain rules, what we end up with is two separate torque components. The first torque component accounts for the acceleration of rotation, and the second is what we define as the torque due to the Coriolis force. Okay, so now we've shown that one way to derive the Coriolis force is by using the conservation of angular momentum. However, while this derivation is clear and efficient, it only provides a partial understanding of the Coriolis force. The only way that you can fully understand the Coriolis force is to understand its intrinsic relationship to changing frames of reference. Today, we will take a closer look at the Coriolis force in spinning reference frames. Ready? Let's go. Imagine a platform spinning around a center point. Unlike the swivel chair, let's have the platform spin at a constant speed omega. Now imagine a red ball standing fixed on the platform. Also, add a blue ball that is rolling on the platform at a constant velocity u in a straight line relative to the platform. Now, this is a really important point. The blue ball is moving in such a way that the red ball, standing at any point on the spinning platform, essentially sharing the platform's rotating point of view, sees the blue ball moving at a constant velocity u. What kind of curve do you think describes the blue ball's motion to an external observer? For instance, a yellow ball standing on the side. It turns out that from the perspective of the yellow ball, the blue ball moves along a spiral path. The constantly changing velocity implies that there must be a non-zero net force on the blue ball. If we can determine the acceleration, then Newton's second law can be used to find the net force. Ready? Let's go. Now let's take several snapshots of the blue ball in motion from the stationary perspective of the yellow ball. Each snapshot is separated from the previous by a small time interval dt. If we examine the velocity v of the blue ball in a given snapshot, we see that it can be separated into two components. One is the blue ball's apparent velocity u from the perspective of the red ball, and the other is the velocity w due to the rotation of the moving platform. As we know, the acceleration a is just dv over dt. So if the total velocity v is u plus w, then a equals du over dt plus dw over dt. So let's start by finding du over dt. To do this, we can collect a bunch of u's from consecutive snapshots in time and gather their tails together at a common center. Since the u vectors would be parallel from the red ball's perspective, their angles are offset by omega dt. This means that as dt approaches 0, the du vector is perpendicular to u, and its magnitude is omega u dt. Dividing by dt and using the right-hand rule, we see that du over dt is omega cross u. Now, let's find dw over dt. To do this, we focus on the rotational velocity vectors w from 2 consecutive snapshots. Again, it makes things easier to bring their tails to the center of rotation. Notice that the triangle spanned by the position vectors and the triangle spanned by the w vectors are similar, but offset by 90 degrees. Since the w vectors are omega cross r, dw is omega cross dr, and dw over dt is omega cross v. So there we have it. When we add the two components, omega cross v and omega cross u, and multiply them by m, we get the net force F. F then splits into two different components. One is the Coriolis force, while the other is the centripetal force. In fact, the centripetal and Coriolis forces come in pairs. One exists in conjunction with the other. In many scenarios, we only see the centripetal force, since often the object is stationary with respect to the rotating reference frame, and the Coriolis force is therefore 0. In this video, we looked at the trajectory of an object moving in a straight line inside of a spinning reference frame. We took a geometric approach to decompose the velocity vector, found the acceleration, and applied Newton's second law to find the net force on the object. Finally, we were able to demonstrate that the Coriolis force exists in conjunction with the centripetal force. So that just about wraps up everything I wanted to cover today. I hope you guys enjoyed what I think is a nice way to visualize the Coriolis force and motion in spinning frames of reference. If you're interested in more, I've left a few graphs on Desmos in the description so that you can interact with the blue ball and the spinning platform. You might also want to think about what happens when the net force is not exactly equal to the Coriolis force plus the centripetal force. What does this mean within the spinning frame of reference?